hydroxide, carbonate and bicarbonate ions. So, these ions can be estimated by titrating against a standard solution of acid using general indicators like phenolphthalein and methyl orange. So, following reactions they will take place during titration. Hydroxide ions present in water, they will combine with H ions of the acid to form water. Similarly, carbonate ions of various salts, they will combine with H ions to form bicarbonate. Bicarbonates, they will combine with H ions of the acid to form water and carbon dioxide. So, this is the general simple acid base reactions, they will take place with sample hard water and standard solution of the acid. So, in first two reaction I have marked here as P. So, P stands for phenolphthalein indicator and M stands for methyl orange indicator. So, we can say for the titration of these two we will use phenolphthalein indicator and for the total alkalinity we will use methyl orange indicator. The titration of given sample of hard water, sample of water stands for that the water whose alkalinity is to be determined. It is titrated against standard solution of acid, like standard solution of acid means that acid whose normality or molarity is known. So, we have taken here n by 100 solution of sulfuric acid up to phenolphthalein end point. Once again the titration of sample water against standard solution of acid up to phenolphthalein end point marks completion of reactions 1 and 2 only. As I have told you just now that if we are using phenolphthalein, so it will show that these two reactions are complete. Whereas titration of sample water using standard acid solution up to methyl orange end point marks completion of all the three reactions 1, 2 and 3. You have seen here that means the reaction of hydroxide ions, carbonate ions, bicarbonate ions with acid, that is complete and we can use for that purpose methyl orange indicator. Hence, the amount of acid used up to phenolphthalein end point corresponds to 1/2 of the carbonate ions plus all the hydroxide ions, and total amount of acid used represents total alkalinity due to hydroxide, carbonate and bicarbonate ions. So, what can be the possible combination of ions which can be present in water and causing alkalinity? That sample water may contain hydroxide ions only. It may contain carbonate ions only, it may contain bicarbonate ions only, or there may be hydroxide and carbonate ions, they are present together, or carbonate and bicarbonate ions are present together. Whereas, the possibility of hydroxide and bicarbonate ions present together is ruled out, because if they are present they will combine to form carbonate ions. You can see in this equation hydroxide and bicarbonate, they will form carbonate and water. So, thus we can say hydroxide and bicarbonate ions cannot exist together in water, and hence all the three types of ions cannot exist together. So, procedure to determine the alkalinity: take 50 ml of sample water in a titration flask, add to it 2 to 3 drops of phenolphthalein indicator and titrate the sample by adding n by 50 standard solution of sulfuric acid from the burette till pink color disappears. To this solution add 2 to 3 drops of methyl orange and continue adding n by 50 sulfuric acid till pink color reappears. So, calculations: let the volume of acid used up to phenolphthalein end point is equal to V1 ml. Let the extra volume after using phenolphthalein end point, the extra volume of acid used up to methyl orange endpoint is equal to V2 ml. Total volume of acid used up to methyl orange endpoint from the starting will be equal to the sum of these two volumes V1 plus V2 ml. Hence, phenolphthalein alkalinity means due to hydroxide and carbonate ions in terms of calcium carbonate equivalents will be this is the total result will be equal to V1 into 50 into 10 raised to power 6 divided by 50 into 100 into 1000. So, on calculating this comes out to be 10 into V1 ppm, and methyl orange alkalinity which is represented as M in terms of calcium carbonate equivalents will be equal to V1 plus V2 total volume of acid used into 50 into 10 raised to power 6 divided by 50 into 100 into 1000. This comes out to be on calculating as equal to 10 into V1 plus V2 ppm. So, this is total alkalinity present in water. Now, the second type of estimation of sample water can be the estimation of total dissolved solids, which is commonly known as TDS. Total dissolved solids means various kinds of minerals present in water. In addition to that, some organic compounds present in water also contribute to dissolved solids. The solids which can be present in water can be the carbonates, bicarbonates, chlorides, sulfates, nitrates and phosphates of sodium, potassium, calcium, magnesium, iron and manganese, etc. So, in simple words we can say these are the salts which can be present in water. Which are these salts? Sodium carbonate, sodium bicarbonate, sodium chloride, sodium sulfate, sodium nitrate, sodium phosphate. Similarly, these salts can be of potassium, calcium and some organic compounds, they may be present in the form of dissolved solids in water. So, we have to estimate the total dissolved solids present in water, what is the amount of these solids. So, these can be estimated or determined in as take 50 ml of 100 ml of filtered water sample means whose TDS is to be determined. So, 100 ml of filtered water is taken. So, evaporate 100 ml of filtered water sample to dryness, further heat the residue to constant weight at 100 to 120 degrees Celsius. After cooling in a desiccator, the dish is weighed. Knowing the weight of the residue, amount of TDS in water sample can be calculated. So, calculation that first of all we take empty china dish. So, let the weight of empty china dish is equal to W1 gram. In it we will take 100 ml of water and that is heated to dryness. Then china dish is again weighed and the weight of china dish plus residue, because now after dryness some white powder is left behind. So, china dish plus residue will be W2 gram. Weight of residue will be now W2 minus W1, that will be equal to W gram. Since we have taken only 100 ml of sample water, so we can equate 100 ml of sample water contains W gram of total dissolved solids. 10 raised to power 6 ml of water sample contains W into 10 raised to power 6 divided by 100. So, W into 10 raised to power 4 ppm TDS. So, this is the determination of TDS in sample water. So, what is this? What is the importance of estimating TDS? The estimation of dissolved solids contents of a sample water is important in deciding suitability of water for boiler feed purposes and also in assessing the quality of water for drinking purposes, because the water for which is used for drinking purposes, it should not contain more than 500 ppm of TDS. So, third type of estimation is estimation of free chlorine. Free chlorine in treated water, if present beyond a certain limit, makes water unfit for drinking purposes. This is because chlorine is injurious to human metabolism. Free chlorine in water is estimated by treating measured quantity of sample water with Ki solution when iodine is set free. The liberated iodine is estimated by titrating the resulting solution with sodium thiosulfate solution using starch as indicator. The various reactions taking place are as such: chlorine plus Ki, KCl plus iodine. Ki also forms a complex with iodine, Ki3. Iodine, which is set free, it reacts with sodium thiosulfate to form NaI and sodium tetrathionate, and with indicator, which is starch, it forms a deep blue complex. So, what is the procedure? Pipette out 50 ml of sample water, add to it 10 ml of 10% Ki, shake the contents well, titrate the solution against N by 50 sodium thiosulfate solution using starch as indicator. End point is blue to colorless. So, this is the calculation. Volume of N by 50 sodium thiosulfate used for each titration is V ml. Volume of water taken for titration is 50 ml. Applying normality equation, N1 V1 is equal to N2 V2. So, N1 is to be determined 50 ml of sample water, N2 of hypo solution is N by 50 and V is the volume used. N1 comes out to be V upon 2500. So, this is the normality of sample water, or we can say normality of free chlorine. Strength of free chlorine will be equal to normality into equivalent mass of chlorine. So, normality is V upon 2500, equivalent mass of chlorine is 35.5 grams per liter. If it is multiplied by 1000, so it will become milligram per liter or ppm. So, strength of free chlorine is, on calculating we will get here 14.2 into V ppm. The fourth type of estimation is estimation of chlorides. In water, chloride ions are present as NaCl, calcium chloride, MgCl2, etc. Although chloride ions are not harmful, but their concentration over 250 milligram per liter impart peculiar taste to water, which is unacceptable for drinking purposes. So, these chloride ions are estimated by titrating sample water against standard solution of silver nitrate using potassium chromate as indicator. When all the chloride ions are reacted with silver nitrate to precipitate out as AgCl, then potassium chromate reacts with excess drop of silver nitrate to form red colored silver chromate, which is the end point. So, these salts which are present as which are contributing chloride ions to sample water, they will react with silver nitrate to give silver chloride as white ppt. At the end point, when there are no more chloride ions, then this indicator will react with silver nitrate to give the red ppt. So, procedure: 100 ml of sample water is taken in titration flask, 2-3 drops of indicator are added and titrated against N by 50 silver nitrate solution. Color changes from yellow to brick red. Calculations: V1 ml of silver nitrate are used. Volume of water sample taken for each titration is 100 ml. Normality equation is N1 V1 is equal to N2 V2. N1 is to be calculated, which comes out to be V upon 5000 N. So, normality of sample water is equal to V upon 5000 multiplied by equivalent mass. So, the strength of chloride ions comes out to be 7.1 ppm. The last of estimation is estimation of dissolved oxygen. Dissolved oxygen is determined by Winkler's method. In this method, so this is all about the estimation of oxygen.